In this video, we'll talk about tree recursion, or branching recursion in Scheme. So the Fibonacci sequence is a nice example of a recursive program. It has a nice recursive definition. So Fibonacci sequence is a sequence of numbers where each successive number is the sum of the two previous ones. So we start with 0 and 1 as our base numbers, and then 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, etc., etc. So the definition of the Fibonacci sequence is as follows. The fib of n is the sum of fib of n minus 1 and fib of n minus 2, unless n is either 0 or 1. If n is 0, then fib of n is 0. If n is 1, then fib of 1 is 1. So it's a nice simple definition in terms of translating this into a recursive program. So here's the code here. Let's just grab this and we'll talk about it in Dr. Racket here. So there's our definition for fib n. So some value n, let's say it's fib of 5, for example. There's three potential cases. Either it's one of the two different base cases, or it's our recursive case. So we have a cond here separating out those three different cases. If n equals 0, it's 0. If n equals 1, it's 1. And in all other cases, we'll call fib of n minus 1, fib of n minus 2, and add them together to get our result. So it's a recursive process because if we do call Fibonacci, we need to do some work on the result. We need to call both instances, so n minus 1 and n minus 2 for Fibonacci, and then we need to add those two results together. So we can't tail call optimize any of this because when it's done, we have to add the results. Okay. So this is called tree recursive because it has this sort of branching structure. It's not a strictly linear recursive process. So the process looks a bit like a tree. If we call fib of 5, that has to calc fib of 4 and fib of 3. In order to calc fib of 4, it has to calc fib of 3 and fib of 2. Similar to calc fib of 3, it has to go all the way down until we get to our base cases. So all the terminal nodes in this tree are all the base cases, and all the internal nodes, or the recursive nodes, are the recursive cases. So substitution model here ends up matching the tree as well. So let's take a look at the substitution model. So if we called fib of 5, just jumping to the active branch of this code would be this. So sum of fib of n minus 1 and fib of n minus 2, where n is 5. And that simplifies to fib of 4 and fib of 3. And now if we're going to simplify this a bit, simplify our effort anyways, instead of going through those whole steps, fib of 4 becomes the sum of fib 3 and fib 2. And fib 3 becomes the sum of fib 2 and fib 1. Close that, close that. And this continues on. I suppose I can do one more branch here before it gets a little bit out of hand. So we got plus, plus, and then to get fib 3, this becomes plus fib 2, fib 1. Closes that. And then we have fib 2, and to get that, it's plus fib 1, fib 0. So that's the left-hand side done. And then on the right-hand side here, we have plus fib 2, which would be fib 1 and fib 0. And then fib 1, which is just itself, so we can just say 1. Okay. And you can continue to expand and contract all of these answers, and the whole thing becomes very hard to read very quickly because the branching ends up having a sort of exponential growth. So the amount of effort to compute this value, fib of 5, or even any larger values, it grows exponentially with the size of n, and it's pretty inefficient as well because there's multiple repeated computations, right? Just looking at this tree, to calculate fib of 5, we had to calculate fib of 3 twice. Fib of 2 had to get calculated 3 times. Fib of 1's got 5 different versions of that. And each time you add to this tree, if we had fib of 6 essentially, this whole tree would exist. We have a fib of 6 up here, and then fib of 4 tree over on the right. So the entire tree effectively pretty close to doubles with each step. Right? If this tree was completely full, it would be order of 2 to the n number of nodes. Now it's not fully full because the Fibonacci sequence always has the left subtree bigger than the right subtree. So technically it's roughly phi to the n, which actually ends up being almost fib to the n in terms of the number of steps that need to be computed in order to calculate fib of n. The space, fortunately, only grows with the depth of our tree because we're only ever going to go down one branch and then collapse up and then go down another branch. So the height of our tree would be the size here, which would be linear with n. But the size of the tree, the number of steps in total, is exponential, essentially. So it's not a very great system. It's somewhat inefficient. So it behooves us then to find a better process to solve this, and it just so happens there's an iterative process. So to compute the Fibonacci sequence using an iterative process, we'll need a whiteboard here, requires a bit of understanding. We have to figure out a way to translate this branching recursive program into something that can be solved essentially using a loop. So let's start off with what we know. So we know fib of 0 is equal to 0. We know fib of 1 is equal to 1. And then for all other values, we know, for example, fib of 2 is equal to fib of 1 plus fib of 0. I'll get rid of the spaces or it'll get confusing. Fib of 3 is equal to fib of 2 plus fib of 1. Fib of 4 is equal to fib of 3 plus fib of 2. And this continues on. Actually, I'm going to put a bit of space here because we're going to need some drawing space. And this continues on, right? So if I did one more, fib of 5 is equal to fib of 4 plus fib of 3, etc., etc. So in order to compute fib of x, we can count from 1 all the way up to x, and all we have to do is keep track of the two previous values. Right? In order to calculate fib of 5, all we need is fib of 4 and fib of 3. In order to get fib of 4, all we need is fib of 3 and fib of 2. So if we start at our base cases, we start at 0 and 1, we can add them up to get 2, and then we can keep track of 2 and 1. We can add those up to get 3, and we can keep track of 3 and 2. And we can add those up to get 4, etc., etc. So long as we're keeping the previous two values, we can just keep doing a repetitive sum and a nice linear iterative process. So the key here is that if we have two values, 0 and 1, as our initial values, one of those values is going to get thrown away, right? We're not going to need this 0 after this first step, but the other value essentially is going to get demoted in terms of, that's a terrible arrow, is going to get demoted in terms of its usefulness, right? Or in terms of its position. And the new value that we computed will replace its old location. And similarly, so fib of 2 comes fib of 3, fib of 3 moves over and fib of 4 comes in. So again, each time we compute this new value, it becomes the seat 1 parameter, and the old seat 1 parameter becomes the seat 2 parameter. So what this means is we can keep track of two values so long as we have a judicious system for organizing which values we're going to move forward from one instance to the next. So we start with 0 and 1, add those up, and keep track of the new value and one of the old values, and those become our two sum values in the next step. So if we want to compute this Fibonacci sequence using an iterative process, let's see if we can't create a program. So define fibit of n. This is the public interface, so the user just wants to know, I want the nth Fibonacci number. They don't need to know all the different helper pieces of information we need to keep track of. But in order to compute this, we're going to have to keep track of the two previous values. So if n is 3, we want fib of 2 and fib of 1. We're also going to need to keep track of what the current value of n is. So if we want fib of 4 versus fib of 3 versus fib of 2. So we're going to have a process that goes from 0 all the way to 5, counting up. And for each of those, we're going to want the two previous fib numbers. So we're going to have a helper function to keep track of all that information. Define helper. We're going to have a counter, and again, that's going to go from 0 to whatever n will be. And then at each of those, we're going to want the two previous Fibonacci numbers, so fib of n minus 1 and fib of n minus 2. Now, this is going to be a recursive program, so we need to have our base case and our recursive case still. So we'll say if, and our base case here will be if our counter's made it to the end, so if counter has passed n, then we return n1. So if, for example, we wanted fib of 4, we're going to go until n is 5, and at that point we'll return the most recent value, n minus 1. Okay. That's our base case, but our recursive case here, so our recursive case, you might be tempted to use something like this sequence here, but we can't do that because we don't want these deferred operations. So the very first thing we should be typing, because that will be the last thing that happens in the expression, should be a call to, in this case, our helper function. Okay. Now the question is, what values do we substitute into C, N1, and N2? Well, if C is our counter, then we're just going to add 1 to it. So the current value counter plus 1. Something for N1 here. Sorry, I put underscores, but they don't show up. But for the N2, so if we have our previous version of N1 was fib1, in the next time through, it'll be N2. Similarly, if fib2 was N1, in the next instance, it's N minus 2. The old N minus 2 just essentially disappears, right? We don't need fib0 after we've calculated fib2. Fib3 is not based on fib0 at all, other than indirectly through these other two values. So the N2 value can just be N1, but we need to put something here, something in this space. I'll use equals so we can see instead of the underscores, which are invisible. So what value should go into this space? What is essentially what is the new n value, right? If we're going to say Fibonacci for n is fib of n minus 1 and fib of n minus 2, then what we're going to do here is compute fib of n and pass that through to become n minus 1 the next time, right? When we compute fib of 2 in this instance, it becomes n minus 1 in the next instance. So to compute the current Fibonacci value, we just add the two previous ones, and then that gets passed into n minus 1. So the next instance, it's a lower seat down, if you will. Okay, so that's the helper function. Now all that's left is to initialize our iterative process to give initial values to these parameters. So the initial values here are how we're starting our search. So we're going to start off at around the 0 mark for our counter. And we have the initial values for 0 and 1. So we're going to call helper here. Helper, we need something for counter, something for N1, and something for N2. So if we're using this repetitive helper function to compute values, it essentially is dependent on the fact that the current value is the sum of the two previous values. But that pattern doesn't work for 0 and 1, right? Those aren't the sum of previous values. They are just themselves the initial values. So if we use those as the two previous values, 1 and 0, then what's the next value we're going to be computing, right? We're not going to be starting on fib0 or fib1 because we already have those values. If we sum those up in this step, what we're going to be getting is fib of 2. So this can be fib of 2. Okay, so we pass 2, 1, and 0 into C, N1, and N2. And then the next step, we'll be calculating fib of 3 between the value of fib of 2 and the value of fib of 1. And the next step, we'll be calculating fib of 4 with the value of fib of 3 and the value of fib of 2. Okay, on and on and on and on. Do the substitution model in just a second, but let's verify that this works first. So run our code. Oh, we left our substitution model out there. So let's call fibit of 5. You can see that's 5, but that's maybe not the most useful value. Let's add 1 to that. So that's 3 plus 5 is 8. If we add those two together, we should get 13 as fib of 7, and that seems to work as well. Wonderful. So in terms of the substitution model, let's see what this process looks like. So we say fibit of 5 is our first question, or our first expression. Again, those are about as simple as they can be, so we'll jump into our code. So fibit says define this helper function, and then this is the expression to evaluate. So helper 2, 1, 0. And now if we call helper with 2, 1, and 0 as these steps, where n is equal to 5 from our initial value there, this will be false, so the active branch of the if statement will be the recursive case here. That's all the brackets. Okay. So let's take this line and substitute our values. So counter is 2, n1 is 1, n2 is 0, and the new n1 will be 1. So if we simplify this, we get helper 3, 1, 1. Okay. And because that's recursive, it goes back through. Again, counter is not greater than n, where n is 5. So we still have a few steps still. So if we call helper with 3, 1, and 1, these are 1 and 1, that's a 1. We can reduce this then, we get helper 4, 2, and 1. And then we call again, we get helper plus 4, 1, plus 2, 1, and 2. So add these together for the new n1 and take this value as it is as the new n2. Okay. We can simplify that, so we get helper 5, 3, and 2. And then again we call helper, so helper with plus 5, 1. Add the two values to get the new fib value, so 3 and 2, and take the old n-1 to become the new n-2 for 3. And we can simplify that. That's helper 6, 5, 3. And because now counter is 6 and n was 5, this is true, and it says return n1, which will be 5. So this whole thing just becomes 5. So notice there's no build-up of deferred operations like in the substitution model up here, where we had all of these expanding fib clauses that needed 2 additional fib clauses in order to be resolved. With the iterative version, we have a nice linear path where, again, if you ignore the intermediate sort of change steps, if you want to call them that, the calls to helper on every subsequent line are the exact same size, but with changing integers. So the process, you can see the current step of the process as the current values here, whereas the current step of the process here is essentially the size of the line, or the amount of expansion that's occurred. With iterative functions, there's no expansion, just a nice changing of variables as we roll through the process. All right, so the number of steps in this process is linear, as you can see. We started at 2 in this case. We counted from 2 to n, so I guess it's essentially n minus 2 number of steps. It's much faster than the recursive fib. We have order of n versus order 2 to the power of n. So the code is maybe not as simple to see, but it definitely will run faster. So it's worth mentioning at this point that there's not always such an obvious translation from a recursive definition to an iterative definition. In this case, it worked out well that we could figure out that if we keep track of 2 values, a nice sequential order to things, we can turn this into a linear iterative process. But that's not always the case. So even though iteration can be a lot faster, it does require a bit more mental overhead to figure out a sort of translation from this very obvious branching structure, a nice one-to-one definition or one-to-one program that matches the Fibonacci definition. It can be a lot harder to make that leap from recursion to a nice linear iteration without putting in the mental effort in between. Okay, so that's it for this video. In the next video, we'll talk about first class and higher order functions in Scheme.